Good morning, everybody. Here's the problem that we have. I can tell you that, for example, I've weighed them, I've got exactly 100 grams, almost exactly 100 grams of red spheres there, and I've got 50 grams of black ones, and that gives you some information. And it's quantified red and black spheres. But you might agree with me that it's actually more visual and perhaps more useful if I tell you that I have 5 red ones and a total of 10 black ones. So often numbers are actually more useful than masses. And indeed, when we look at chemical reactions, what we're interested in is, for example, let's say we have 2 hydrogen atoms combining with 1 oxygen atom to give 1 molecule of water. We're looking at numbers combining, not masses. The difficulty is, in the lab, we have instruments, balances, that weigh things, that give us a mass. There isn't an instrument that can give us a number of a material. But all is not lost. How can we make the connection between a mass of a substance and the number there, or the number of the substance, when that substance is so small that we can't count it, such as an atom, a molecule, for example. Now, quick reminder of our model for the atom. All the mass is focused in the nucleus of the atom. The volume of the atom is given really by the number of electron shells that are filled or partially filled, and the electrons are there, but the electrons have very, very little mass compared to the mass of the protons and the neutrons. And if I look at, say, the mass of a hydrogen atom, 1.66 times 10 to the minus 24 grams. The mass of a typical uranium atom, heavier than that, 3.95 times 10 to the minus 22 grams. Why should they be different? Well, they're different because they have different numbers of protons and neutrons in the nucleus. A typical hydrogen atom has just a single proton in the nucleus. A typical uranium atom has 92 protons and about 146 neutrons in the nucleus. And actually, if I look at the ratio of these masses, I find that they work out to be a figure that indicates a uranium atom is 238 times heavier than a hydrogen atom. The sum of the number of protons and neutrons in a uranium nucleus is 238. So it's not surprising that it's 238 times heavier. If I think about some of the other elements in the first row of the periodic table, if I think about, say, lithium, it has 3 protons and 4 neutrons in the nucleus. So it's going to be 7 times heavier than that of a hydrogen nucleus. If I look at, say, carbon, then we find that carbon has 6 protons in the nucleus and 6 neutrons, giving a total mass of 12. So a carbon atom will be 12 times heavier than that of a hydrogen atom, and so on and so forth. We can relate the number of protons and neutrons in the nucleus directly to the mass of the atom. Now, if we look at the periodic table, we find that the number underneath the element indicates what we call the relative atomic mass of that element. And the first thing you notice probably is that it's a non-integer value. So something like silver down here. It has a value of 107.87. And you think, well, that's a bit weird, because how can I possibly get 0.87 of a proton or of a neutron or some other combined fraction? So we're probably comfortable with the fact that heavier atoms have more protons and neutrons, and we can say that they're heavier by a certain amount related to those subatomic particles. But what we also must take into account is that when we deal with atoms, we're dealing with the whole bulk of them on a macroscopic scale, on a scale in which we live. We have millions upon millions of atoms, molecules, particles that we deal with all the time. And as a consequence, we cannot help but deal with an average of all possible isotopes of that element. So most elements have two or more isotopes. And a quick reminder, an isotope is where you have atoms of a particular element, so the number of protons is fixed, but the number of neutrons can vary a little bit. And let me show you how this might work. If I take, say, a natural sample of silver, I find that there is contained in that sample two isotopes of roughly equal amounts. So any sample of silver contains just over half of the isotope silver 107. And this calculation I've put on the top of page 3 of topic 7. And just under half, 48.16%, of silver 109. So, if I look at a weighted average of the mass of the silver atoms, then combining these, (51.84% of 107 plus 48.16% of 109 equals my average mass of a silver atom, 107.9, and that is the figure that's in the box below the symbol in the periodic table. And if you look at almost any element in the periodic table, it is a non-integer value for mass. That does not mean that there are non-integer values for numbers of protons and neutrons in the nucleus. What it does mean is that that element has a range of isotopes in its natural form, and that we observe an average mass. Well, how do we proceed from here? If we want to look at the periodic table in terms of relative masses, then in many ways the obvious one to choose as the basis of this would be hydrogen. And for a long time hydrogen was chosen as the baseline against which we measure other atomic masses. And it was taken that, let's say we have 1 gram of hydrogen atoms. We could then say, okay, if we take 107.9 grams of silver atoms, that will contain the same number of atoms, because on average a silver atom has a mass that's 107.9 times greater than that of a hydrogen atom. But the scale based on hydrogen was not terribly convenient, because hydrogen's a gas. It's much easier to use solids, and nowadays we base this relative scale on carbon, and we say, let's take the number of atoms that we have in 12 grams of the isotope carbon, carbon-12. And let's say that's a special number, and take that same number of atoms of any element and look at their mass, and we find that that mass will contain the same number of atoms. It will be bigger if the element is beyond carbon in the periodic table. It will be smaller if the element is before carbon in the periodic table. That number is what we call the Avogadro number. Sometimes it's given the symbol N subscript A, the number of atoms in exactly 12 grams of carbon-12. It's actually a huge number of atoms. The Avogadro number equals 6.022 times 10 to the 23. But how do we use this? What it says is that imagine we've got a sample of 12 grams of carbon-12. You might be looking at the periodic table and say, but under carbon in the periodic table it says 12.01. And that is correct, because in a natural sample of carbon, though it's 99% carbon-12, there is about 1% of the heavier isotope of carbon, carbon-13. And as a consequence of that, the average mass of the Avogadro number of carbon atoms is just a tiny bit over 12 grams. So we define the Avogadro numbers as exactly 12 grams of carbon-12, but of course we deal with a source of carbon that comes from nature that contains the other isotopes as well, and so we have just over 12 grams of carbon-12. If I look at some of the other elements in the periodic table, I can say hydrogen atoms are going to be 1/12 the mass of carbon-12. And if I take 1 gram of hydrogen atoms, that will have the same number of atoms as its Avogadro number. If I take, let's say, 238 grams of uranium, or specifically of one of the isotopes uranium, that will have the same number of atoms as there are in exactly 12 grams of carbon-12. We call this, or this concept, we call it the mole concept. It's a scaling factor that enables us to take atoms, molecules, from an atomic scale up to quantities that we can measure in the lab. If I want to combine hydrogen with oxygen, I can't do it on an atom by atom scale. I have to do it on a scale that I can measure the material out. Let's say I have 2 grams of hydrogen atoms. I would need to combine those with, for example, 16 grams of oxygen atoms, because oxygen is 16 times heavier than hydrogen, and I need 2 lots of hydrogen for every 1 lot of oxygen. I can write a formula for this where I say the amount of material, and we use amount very specifically to indicate numbers. The amount of the material is the mass divided by what we call the molar mass. It's the number of entities divided by the Avogadro number. So, how does this work? Well, let me just show you some typical elements. If I look up the periodic table, I find magnesium has what I'll call a molar mass of 24.3 grams. So 1 mole of magnesium atoms weighs 24.3 grams. That contains the Avogadro number of magnesium atoms. And that's the same number of atoms as there are in 63.5 grams of copper, or 65.4 grams of zinc, or 27 grams of aluminium. What do we got here? Lead. 207.2 grams of lead contains the same number of atoms as those other quantities of the other elements. And similarly, sulfur, 32.1 grams. It's a light material at the top of the periodic table. Carbon, 12 grams, we've seen before. Tin, 118 grams. All these samples then, they have different masses, but I can be confident that they all contain exactly the same number of atoms of that element. And if we want to determine the number of atoms, we can use this formula. The mass is something we weigh. The molar mass is something we look up on the periodic table. The Avogadro number is something that's fixed, and we can determine the number of atoms that we have of that material, the number of units we have. Now, I'm going to use the term molar mass throughout this. There are a range of terms when we're talking about atoms, sometimes called atomic mass. If we talk about molecules, it might be molecular mass. Talk about ionic materials, it might be gram formula mass. I'm going to use the term molar mass to indicate something about this scaling factor, whether the material be an element or a compound, a molecule or an ionic material. So let's see how that might work. If I take 1 gram of hydrogen atoms, that then contains the Avogadro number of atoms. However, that's not the natural form of hydrogen that we have around us. Hydrogen occurs as a diatomic molecule. And if we want to determine the molar mass of a molecule, we need the formula, we multiply by the appropriate amount of each atom in the formula. So that 2 grams of H2 molecules also contains 6.022 times 10 to the 23 units, and this time the units are molecules. So the Avogadro number doesn't necessarily refer to atoms or molecules. It could refer to anything. It could refer to ions. It could refer even to electrons, as we'll see. If I say, look at oxygen molecules and ask myself, what is the mass of 6.022 times 10 to the 23 molecules of oxygen? I would look up the periodic table and find that for oxygen atoms, O on its own, it says 16 grams. So for an O2 molecule, I double that. So okay, 32 grams of oxygen molecules contains this Avogadro number of molecules. If we have this Avogadro number, we call it 1 mole. All these quantities and if we think about the origin of the word mole, mole means large number. Molecule, or maybe I should pronounce it molecule, means individual particle. So it's a large collection. So when we're dealing with moles, we're dealing with large collections of molecules, atoms, ionic materials, whatever. If I look at an ionic material, let's take sodium chloride. Now we've seen that when we write formula, then in terms of ionic material, we always write the lowest ratio of ions. But we recognise that a sample of sodium chloride is made up of millions upon millions of sodium cations and chloride anions in a three-dimensional array. If I want to calculate the molar mass of sodium chloride, we do that from the formula. I look up the periodic table, find that the molar mass of sodium is 23.0. The molar mass of chlorine, 35.45. Let me call it 35.5 here. Overall then, I have a molar mass of sodium chloride 58.5 grams, and what that means is that if I take a sample of sodium chloride weighing 58, and here's one, 58.5 grams, looks like that, that will be 1 mole of sodium chloride. It will contain 1 mole, that Avogadro number, of Na plus ions and 1 mole of Cl minus ions. Similarly, I can do the same sort of calculation for potassium hydroxide or sodium hydroxide, 2 other materials. Potassium is lower down the periodic table than sodium, so if I have a salt, the same salt of both of them, it's no surprise that the potassium hydroxide for the same number of ions is going to be heavier than that of the sodium hydroxide, 56 grams versus 40 grams there. If I look at water, H2O, 1 mole of water is going to have a molar mass of 2 times 1 plus 16, or 18 grams. Assuming the density is 1 gram per milliliter, then 18 mils of water represents exactly 1 mole of water, and as a consequence of that has 6.022 times 10 to the 23 molecules of water present. And there's another couple of samples. And we can do this for any material. How do we use this in calculations? Well, let's take sodium chloride as an example, and just to do the calculation at the top of page 7 of this topic, imagine you've got a small container of salt that you buy at the supermarket. Very typically, that will contain 125 grams. So we could ask the question, how many moles of salt are there in 125 grams of sodium chloride? We can use the formula that the amount, an amount in chemistry is very specifically means the number of moles a formula that I'd like you to learn is the amount is mass over molar mass. In this example, we have a 125 gram container of salt. The molar mass of NaCl is 58.5 grams per mole. Might represent it like that. I do the calculation, I get a value, and I have a unit of mole. So a small container of salt contains just over 2 moles of salt. Moles is something, a quantity that we use a lot in chemistry, and the symbol we use to donate a number in moles is just MOL. So it's not much of a shortening from MOLE, but nevertheless convention is MOL indicates the number of moles of a material. So if we think about an element, if we refer to a mole of sulfur, shall we say, what are we referring to? Well, we can take our knowledge of how we write the chemical formula of the element. Here, if I refer to 1 mole of sulfur, then we imagine it as sulfur atoms. We know that as a solid that it's an aggregate, but we know that 1 mole of sulfur is 6.022 times 10 to the 23 atoms. If I take, on the other hand, one of the gases, say oxygen, one of those elements that always forms diatomic molecules. If I say 1 mole of the element oxygen, then what I'm referring to is 1 mole of O2. And what I have to do is say, okay, 1 mole of O2 equals 2 times the figure on the periodic table, which is 16. So 1 mole of O2 has a mass of 32 grams. That contains the same number of molecules as there are atoms in 32.1 grams of sulfur, or 12 grams of carbon, and so on. Now, to just highlight a couple of examples, if I want to determine the mass of 1 mole of carbon dioxide, I would need a correct formula. In this case, it's given CO2. I would need a periodic table in order to look up the molar masses of the atoms. And this is really why we want you to learn some of the elements of the periodic table, so that you can instantly go to carbon on the periodic table and say, okay, 2.01 is the molar mass of carbon atoms. I look up oxygen, and on the periodic table, it's the molar mass of oxygen atoms that is given, 16.00. In carbon dioxide, there is 2 of them. So I need to multiply that by 2, and overall, I then get a mass of 44.01 grams represents 1 mole of carbon dioxide. And I can do this for anything I like, and let me do just 2 more examples. In fact, what I'll do, I'll modify the example a little bit from the one in the book, example 3 on page 9. It says, what is the mass of 1 mole of C12H22O11? I'm going to modify that a little bit and say, what is the mass of half a mole of C12H22O11? This formula is actually the formula of sucrose, not something I need you to remember. Let me start off by using the formula. The amount, or the number of moles, is the mass over the molar mass. So that's our basic formula. I always remember it in this form and then rearrange as necessary. In this equation, I want the mass, so rearranging this, mass is number of moles times molar mass. I can now put in the figures. 0.5 moles is what I'm interested in for the question. The molar mass I get from the formula and the periodic table. 12 times the molar mass of carbon plus 22 times the molar mass of hydrogen plus 11 times the molar mass of oxygen. And if I work that out, I find that this comes out to be 342 grams per mole. 0.5 times 342, 171 grams. So, half a mole of sucrose weighs 171 grams. Let me finish showing you one equation and looking at molar quantities. And this relates to the example 7. And it says, how many moles of each of the constituents are there in 1 mole of sodium sulfate? Sodium sulfate is an ionic material. If I split it up, I will see it is composed of 2 lots of sodium ions and 1 lot of sulfate ions. Sulfate is one of those polyatomic ions. That means there's a collection of atoms covalently bonded to one another, all of which have a charge. And for polyatomic ions, they don't break up any further. So 1 mole of sodium sulfate contains 2 moles of sodium ions and 1 mole of sulfate ions. If I were to have a look at masses and work out the masses, I find that the mass of 1 mole of Na2SO4 is, of course, the same as the mass of 2 moles of Na and 1 mole of SO4 2- ions. You don't get rid of masses, but bear in mind that the numbers of particles may change. We're going from, if you like, units to the constituent parts. We will use this when we look at calculating the amount of material we'll produce in a chemical reaction. So to summarise this mole concept then, atoms have different masses as a result of different numbers of protons and neutrons in the nucleus. In the lab we can weigh masses. We can't count atoms at all easily. In the lab we can only work on what we call a macroscopic scale, a scale that we can see, a minimum of 1 gram or maybe a small fraction of a gram. We can't work with individual atoms and molecules. So we need a scaling factor to bring things up from a microscopic, an atomic scale, to a lab scale. That scaling factor is the Avogadro number. We'll scale everything up in a way that 6.022 times 10 to the 23 units of that material bring it onto a scale we can easily measure. We call that number of units 1 mole. 1 mole of hydrogen atoms weighs 1 gram. 1 mole of hydrogen molecules weighs 2 grams. 1 mole of sucrose molecules weighs 342 grams. Those quantities, those masses, may be different. The number of particles, whether they be atoms or molecules, are the same in all cases.